Okay, page 16 of the scheduling notes. Let's just talk about the implementation of a timeline schedule. You have this fixed order that the tasks are going to execute in, and probably the simplest way to do it is to put the function pointers into an array. So an array of function pointers, and so you're going to see this in problem set 4. I think it's the first question I ask you to actually implement such a schedule, and it's actually not too complicated. So I couldn't remember why I was teaching you function pointers before, except that you use them when you create threads. Well, this is the other reason. So now I remember why they're useful. So just to give you an idea, from our current example, we had task 1 ran first, so you could have a pointer to task 1. We could just call it T1, and then T2, if you're just looking at the scheduling template we just filled out, and then T3 ran, or sorry, T1, T3, and then it was T1, T2, T1. I see I didn't leave myself enough room here. And then the order that I chose was T3, and then T1, and then T2. And so we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 entries. The runtime scheduler overhead, if you look at the implementation, you have a for loop. You've got an index into the array, and you invoke the function that's being pointed to in the array. When it returns, you move on to the next one, and the number of operations is order 1 for each new task that you're scheduling to run. So it's very lightweight. So there is some storage required to implement this, and it's going to be related to the array length. And we can calculate the array length algorithmically or analytically. And so you can see that T1 occurs 1, 2, 3, 4, 5 times in there, which happens to be the schedule length divided by the period of T1. So the array length is equal to the sum for I equals 1 to n for each of the tasks of the least common multiple, the schedule length, over the period of task I. So in our example, that's 90 over 18 plus 90 over 30 plus 90 over 45 gives you 5 plus 3 plus 2 gives you 10. So in our example, that wasn't too bad. The storage required can be large. So let's just say, for example, our task set has 5 tasks. T1 is 18, has a period of 8. Task 1 has a period of 18, task 2 has a period of 30, task 3 has a period of 45. So that's the same as before. And I'll just write these next two. So T4 and green. So period of task 4 is 22, period of task 5 is 23. So then the least common multiple is equal to, well, so if we look at the prime factors of T4, 22, that's 2 times 11. Those are the two prime factors. And the prime factors of T5 are singular, it's 23. So we're going to have 2 times 3 squared times 5 times 11 times 23 equals 22,770. So the schedule length is now a lot bigger, and the array length needed to store the schedule is, I'm not going to write it all out, but it is 4555, so it's a lot bigger than 10. So if you run into this kind of problem, a trick you can use to shorten the array length is to shorten some of the periods so that they have a shorter least common multiple. So generally it's usually okay to shorten the period of a function to make it run more often, as opposed to lengthening the period if we're trying to come up with a nice least common multiple. So it's often okay to shorten the task period. And so if we do that, say we change, so the period of task 5 was 23, let's make it 22. That's still pretty close to the original. And now the least common multiple is just going to be 2 times 3 squared times 5 times 11. So 90 times 11 is 1980. And the array length is going to be equal to 400, which is a fair bit shorter than 4,000.